sphere up to about 4 revolutions per second, and the inner core up to about 15 revolutions per second. So let's go give it a spin.
If it succeeds, Lathrop's experiment will advance our understanding of how our magnetic field is generated.
Looks good. Seeing 26 tons of rotating metal and liquid up close and the sound, really had no idea it would be like that. It's rather intense.
As the vast sphere reaches maximum speed, something incredible happens. Huge lines of magnetism arc in and out of the model core.
While we can't see the magnetic fields coming out of the experiment, we can measure them. We can put many different magnetic field sensors and then map out these magnetic field lines coming out, rotating, changing. It's fantastic.
Interactions between the inner and outer core create what's known as a dynamo. This generates a powerful, stable, and self-sustaining magnetic field.
This is showing magnetic field patterns, red coming out of the experiment, blue going into the experiment. It's nothing like I imagined it would be.
Lathrop's mechanical core supports the theory that Earth's magnetic field is produced by a geodynamo in its interior. The motion of liquid metal in the outer core is vital to this process. The geodynamo depends on the flow of hot molten metal in Earth's core. Does Mars's cold core explain how it lost its magnetic shield? Could Earth suffer the same fate as Mars?
So cooling is going to continue, and eventually the Earth's solid inner core is going to grow larger and larger and larger. At some point, it may solidify completely, and it's possible that even before it solidifies completely, the Earth's magnetic field will shut off.
Is the South Atlantic anomaly a sign that Earth's core is cooling? Lathrop doesn't think so.
People think about the Earth's magnetic field as just being north-south, right? You have a compass, it points north. Everything's simple. But if you look carefully on maps, you notice that magnetic north and geographic north are not the same thing. Now that's in part because the magnetic pole is actually in Canada.
The magnetic North Pole is elusive. Whenever explorers look for it, they find it in a different place. Larry Newitt from the Geological Survey of Canada charts the movement of the magnetic North Pole as it wanders the icy reaches of northern Canada.
To determine where the magnetic pole is, we can't rely on one single observation. What I try to do is surround the estimated position of the pole, taking as many observations as possible.
This wandering is symptomatic of fluctuations in the geodynamo, but in recent decades, scientists have noticed that the pole has been moving faster.
Over much of the past 100 years, it's been around 10 kilometers per year. But since about 1970, it started to accelerate, and now it's moving along at about 40 kilometers per year.
In around 50 years' time, it might reach Siberia. So does the wandering pole's acceleration have any connection with Earth's weakening magnetic field? Professor Jeremy Bloxham is searching for an answer. He uses the records of early sailors to chart the magnetic North's movement over the past 300 years.
Because of the importance of the magnetic field to navigation, people on trading ships and voyages of exploration back in the 17th century or the 18th century were making very careful, systematic measurements of the magnetic field.
Bloxham feeds the historical data into a computer, which creates an impression of Earth's magnetic history.
What we have here is an animation that will show us how the field has changed over the 300 years or so since 1690. And in the shades of red and orange, we're showing the strength of the magnetic field as it comes out of the core, and in the shades of blue, the strength of the magnetic field as it goes back into the core.
Over the last 150 years, scientists have measured a 10% decline in the overall strength of Earth's magnetic field. It's fading 10 times faster than if the geodynamo suddenly stopped. But crucially, parts of the field are behaving differently.
Now, as we get into the beginning of the 20th century, we begin to see the emergence of this blue patch here beneath southern Africa, which then drifts to the west and joins up with this other patch, making a large region at the core mantle boundary where the field is going in the opposite direction from what we would expect.
Bloxham's computer model reveals that at the South Atlantic anomaly, the magnetic field isn't just weaker than anywhere else on the planet. It's actually reversed polarity.
There's a patch on the core in the South Atlantic where things are not pointing as they should be. They're opposite, and that patch is growing.
Where the magnetic field has reversed, lethal cosmic radiation that is normally deflected away from the Earth is getting through. The South Atlantic anomaly stretches over 3 million square miles. It extends over much of South America. Radiation currently reaches the upper atmosphere, so it mostly affects our spacecraft and satellites. But if the anomaly continues to grow at the present rate, one day it will reach us.
What's clear is there is storm brewing, if you will, under the South Atlantic.
The storm is only just beginning. If it grows, our vital protection against solar radiation will shrink. The sun will turn from being our friend to our enemy. If our magnetosphere disappeared, high-energy solar radiation would gradually strip our planet of its atmosphere, water, and life. The stakes are high. To prepare for the future, we need to take a closer look at the past.
T-minus 15 seconds. Guidance is internal. 12, 11, 10, 9. Ignition sequence start.
July 20th, 1969. Neil Armstrong is the first man to set foot on the moon. It's one of mankind's greatest achievements.
The Eagle has landed. Roger, Tranquility.
But during the mission, Armstrong and co-pilot Buzz Aldrin see flashes of light inside the darkened Apollo 11 module. Bizarrely, they even see the flashes with their eyes shut. When they return to Earth, they report what they saw. NASA scientists are mystified. 6 years later, they come to believe these light flashes are the result of high-energy, heavy cosmic rays penetrating the spacecraft and the crew members' eyes.
They're just protons, electrons, just very, very high energy, ripped apart atoms spraying out from the sun. In terms of manned space travel, if you're outside the magnetosphere in a big solar storm, large amounts of radiation passing through your body, dire health consequences.
These particles can become trapped inside a region of the magnetosphere known as the Van Allen belt. They present a real hazard to astronauts. Astoundingly, at least 39 astronauts have developed some kind of eye cataract 4 or 5 years after exposure to this dangerous radiation. As our protective magnetic field weakens, the risk to life increases. Professor Gary Glatzmeyer wants to know how much weaker the Earth's magnetosphere is going to get. He creates a remarkable computer model of Earth's magnetic field.
We can't reproduce exactly what the Earth has done in the past or what it's doing right now. What we're trying to do is get the model to simulate something that's qualitatively similar.
Glatzmeyer runs the computer model continually. Each year of real time represents 100,000 years of simulated time. He observes how the magnetic field evolves over the millennia. Around 36,000 years into the simulation,